x, and didn't we see this one already? This is the same as sine x minus, or we saw something very similar to that. Is it still up there? I think we erased it, but yeah, that may ring a bell, right? And so, I think we did it like this, right? We said, well, plus or minus 1 minus cosine squared. It wasn't exactly this, right? But this would be 1 plus cosine x then. And if we square both sides, if these things are equal, their squares are equal. This gives us 1 minus cosine squared x equals 1 plus 2 cosine x plus cosine squared x. And so 2 cosine squared x, am I skipping too many steps here? Minus or plus 2 cosine x equals 0. So I'm just grouping all the terms on one side, and think of grouping them on the right side and then swapping the sides. Right? And that's the way it would come out, right? So I can then divide both sides by 2 and factor out cosine x. And say, well, either cosine x equals 0 or cosine x equals negative 1. Is that true at these points? Here cosine x equals 0. Here cosine x equals negative 1. Right? So where is that on the unit circle? That's I guess see, we would get extraneous solutions here, right? Because cosine x is also 0 at 3 pi over 2, right? Is 3 pi over 2 a solution? No, they're far apart at 3 pi over 2. In fact, they're opposites. You got 1 and negative 1. This is what we ended up squaring on the left and the right sides, right? Yeah. So that one is out, right? So so we reject these places where cosine is 0 and accept only these. So the graphical solution gives you a more clear idea of where it's true. With the algebraic one, you end up having to equate squares, in which case you got to check that all solutions work in the original equation, and that's going to be a little bit more work. With the graphical approach, it's readily apparent. Okay. Questions about that? Is that good? So there's 38, 42. Here we got problems. Because we got two different angles, right? We got 3 theta and we got theta. I think if we think about this in the right way, it'll be easy. So 42, sine 3 theta, cosine theta, minus cosine 3 theta, sine theta equals 0. I think it's 42. Forty-four, 42. Oh, did I switch them around?
Yeah.
I did. So this is sine and cosine. Here is sine, here's cosine, and this is sine, and that's cosine.
Wait, no.
It's still wrong?
Yeah, it's.
No, I just reversed the factors.
Yeah.
Right, so it's sine 3 theta, cosine theta, minus sine theta, cosine 3 theta. That's the same as sine cosine 3 theta, sine theta, right? Equals 0. So is it obvious what to do here?
It's the sine of 3 theta minus theta. But
Yeah.
I don't know how to do it.
Right. 3 theta minus theta, right? So that's alpha minus beta. Sine alpha minus beta is sine alpha cosine beta minus sine beta cosine alpha. And then we can just combine these guys, right? You get a very simple equation.
Oh, 3 minus 1.
Yeah, right. Just combine like terms. Yeah. So, And that is gonna say, well, 2 theta is where sine theta is equal to 0 at any multiple of pi. Right, so first solve for the multiple of theta, and this is a pretty simple one, right? Because it's just any multiple of pi is where y equals 0 on the unit circle, right? Here, and here. Zero, pi, 2 pi, 3 pi, 4 pi, 5 pi. And so then solve by dividing by 2, you get, here, so north, south, east, and west. All those points. And, you know, maybe try one and see that it works. Pi over 2, sine 3 pi over 2 is 0. Cosine 3 pi over 2 is 0. Cosine pi over 2 is 0. Cosine 3 pi over 2 is 0. 0 minus 0 equals 0. If pi, well, sine 3 pi is 0. Sine of pi is 0. So, if, you know, both north, south, and east, west, one of these two sines or cosines is 0. So 0 minus 0 is 0 all day long. 46, we get, again, a mixture of things. Tan theta plus cotangent theta equals, well, let's move on, because I think we've done one very similar to that. How about 48? Here we got twice the square of sine plus 2 more than cosine twice theta. 48. Twice the square of sine minus cosine twice 48. Equals 2 more than the cosine of twice theta. There's our equation. Should we choose to accept it, we can solve it. All right, so we've accepted it. Now we have to solve it.
Change that to cosine.
Yeah, I think that the big stumbling block here is we got theta and 2 theta at the same time. You just want one or the other.
Oh.
So we can go either way. We could write this as one of the 3 double angle identities for cosine. There's one involving only sine, right? Namely, cosine 2 theta is 1 minus twice sine squared theta. Right? That identity. In which case we get 3 minus twice sine squared theta, right? So add geez, they always have it come out so nice. The real world things don't work so nicely. But yeah, we get benchmark values, right? So I would say at this stage it's a good idea, dial them up on the circle. Let's have an idea of that. So, right, so pi over 3 is one place where sine is equal to the positive square root of 3 over 2, and then 2 pi over 3 is a place in the second quadrant where that's true, right? So we have these two solutions, the angle and its supplement. And then they're opposites, right, down here. That's where it's negative square root of 3 over 2. And I guess we could call this negative pi over 3 and negative 2 pi over 3. I mean, that works. There are other angles coterminal with those. But I mean, if you dial it up on the circle, then it makes it easier just to say, look, theta could be plus or minus pi over 3 plus any angle coterminal with those, or theta could be plus or minus 2 pi over 3 plus any angle coterminal. There's a lot of different ways of describing these, right? There are those. What else could you say? I suppose pi over 3, 2 pi over 3. Is that 5 pi over 3 and 4 pi over 3 and 5 pi over 3? Yeah, this is 2 pi minus 2 pi over 3. And so go around 2 pi and come back. That'll give you 4 pi over 3, and this is 5 pi over 3. Yeah. So you could go with those as well, but if you want to write it in nice compact form, this is sort of convenient, right? So you can say plus or minus this, or plus or minus that. And that's great. Well, I guess we could also gotten this with the other identity, right? So how would that work? Same equation. Here, well, here, for sine squared, we can write, well,